Awesome. All right, cool. Well, we'll go ahead and get started now. Audio sound okay, Alex? Too loud? Too little? All right, perfect. Awesome. Hey, you look good to me.
Well, thank you.
You bet.
We should go have a beer.
So I was going to chat a little bit about NoSQL. And when I do this, I like to usually start a presentation off by kind of polling the room, getting an idea of who thinks they're a good expert in NoSQL? Who thinks they really know the landscape? No one's so ambitious. All right, some of you think it. You just don't want me to call you out. That's fair. How many of you have at least dabbled in it? Done something with a NoSQL database? Okay, that's a surprising number. How many of you know what I'm talking about when I talk about NoSQL models? Okay, all right, awesome. Well, that's a pretty good sampling. So before I kick this off, I have to turn on my presenter thing. Before I kick this off, I like to start with a disclaimer. It's been about 2 years since I've done this presentation. This is something I did back in the Chicago office. And when I kicked it off, it was actually a brown bag series. This is 5 different brown bags condensed and distilled into one presentation. So what that means for this is that this is very much the 100 level course. We're going to cover all the different models. We're going to talk about why those models are important, but we're not going to get into some of the 300 and 400 level stuff. We're not going to get down into the read and write paths of Cassandra. We're not going to talk about cap theorem. We're not going to talk about acid versus base. Content exists for all of that, though. We have brown bag content around all of that. It's tough to do that in an hour. And if you did, most of your heads would be spinning by the time we were done. So we keep it very simple here. We're going to talk only about the models and really their use cases. That said, I think you guys still get a lot of benefit out of it because it's really helpful to understand these. So if I'm not talking about all those interesting things, why am I talking about it at all? We do have some pretty top-level goals here. Number one, I'd like to establish a common vocabulary for everyone in the DC. When we start talking about NoSQL, I'd like us to all be using the same kind of words. I'd also like to kind of foster a general competency around the main NoSQL models, the main 4 that we'll get to in a moment. And I think the first 2 will better enable us to talk to ideas of data modeling, database selection, and data management with clients, because ultimately that's what matters, is that you can talk intelligently to these subjects with a client. You don't have to have the depth, but at least we'll cover the breadth here. Where I like to start is defining NoSQL. There are some common definitions out here, and full disclosure, they are all terrible, which is part of the problem. We'll start with the very first definition. This is the one that came out when the very first few NoSQL databases were introduced, some of the very brand spanking new ones. We started off with a definition was that these databases are any database that does not utilize SQL, the literal definition of the word. If it doesn't have a SQL interface, we'll call it a NoSQL database. The problem is, as these databases progressed, that became less and less true. Now, it's flat out misleading. Do not use this definition of the word. You can think about Cassandra, because you can do a query like this in Cassandra. Looks like SQL, right? Yeah, and OrientDB still looks like SQL. And even in databases that are classically considered SQL databases, like MySQL. If you guys have ever played around with the NDB clusters in MySQL, they have an API that is non-SQL. That doesn't make MySQL a NoSQL database. That's stupid. So clearly we can see that this definition doesn't work, doesn't cut it. So it evolved over time. We took a different approach. We got a little bit smarter, and we said, all right, now it just means non-relational. NoSQL is any database that doesn't have a relational component. And this was a step forward. This was improving. It accounted for a lot of NoSQL databases out there. The problem was it still didn't capture all of them. There's a particular database model in the NoSQL world that is, in fact, exceptionally relational. You can take the property graph model, for example. These are 3 different records that are linked together using relationships. Tough to look at that and say that that's non-relational. These 3 entities are clearly related to one another. You can take it even one step further and look at a full-featured RDF graph. Pretty darn relational when you get down to the heart of it. So to simply dismissively say NoSQL databases are those that have no relationships, that's clearly not covering the full breadth of the NoSQL landscape. So then we got clever. Then we got really creative. And we came up with this third definition. This one is clever on many levels. First of all, you can see that we turned NoSQL into an acronym. Now the no stands for not only. Not only SQL. And everyone in the community was so proud of this definition. And now they say, no, not only SQL databases include databases that provide a mechanism for storage and retrieval of data that is modeled in means other than the tabular relations used in traditional relational databases. It's the most legalistic term we could find for NoSQL, but it's the one I hate the most. And I hate it because it's the most meaningless definition we could have come up. It's a lot of words, but they're words that ultimately say nothing. And I'll give you an example of why this makes no sense. Imagine you were talking to somebody who had never tasted an orange. And you were trying to describe to them what it means to eat an orange. And the best definition you could come up with is, well, I can tell you one thing, it doesn't taste like Chilean sea bass. That would not get them any closer to understanding what an orange tastes like. The problem there is that you can't define something by listing exactly one thing that it is not. Nobody else would accept a definition like that. If you sat in front of a client and tried to explain NoSQL to them and said, well, I can tell you one thing, it's not MySQL. They would say, thanks, but what is it? So that's a long list of things that you probably shouldn't use to describe NoSQL, and you're probably all thinking right now, all right, fine, you've gone through the long list of things you told me I can't do. What is NoSQL? Is there a right definition? Spoiler alert, there isn't. There is not a single one definition that I'd like you guys to use. The problem with NoSQL is that it's too broad of a term. It was too ambiguous because it tries to cover too many things. You can't summarize in exactly one word everything that NoSQL covers. But as it turns out, 4 words actually cover it pretty well. Those 4 words are these NoSQL models: key value, document, columnar, and graph. And for those pointing out that key value is technically 2 words, so technically I have 5 here, to you I say shut up. KV, if we abbreviate it as KV, it works. 4 words. So let's dive into some of these. Let's talk about key value databases first. They're the easiest ones to wrap your head around. That's why I like to start here. Basically, a key value database is a simple association of keys and values, any arbitrary key and any arbitrary value. There is no constraint on what that value is. It can be a file. It can be a structured document. It can be unstructured content. There's a wide variation in the implementations there. It's also important to note that key value models often serve as the building blocks for some of our more advanced models. As we look at some of the other ones, you'll see that a lot of those do have key value pairs. They just happen to have more. So when we talk about key value databases, databases that are strictly key value, you're looking at things that literally can only look up by a single key. That's kind of their defining factor. And their advantage is that they do that extremely fast. You guys can think of a shopping cart site or a session cache or any of those things that you have to do extremely fast lookups by a single key. There's a lot of use cases for those out there. And that's their bread and butter. That's where they perform the best. And that's why they're often in memory. So in memory for the fastest operation. This is why this is where they really get a leg up on traditional SQL databases, is that all of this is stored in memory and they've been optimized for these single key lookups. They don't worry about the overhead of additional indexing. There's only one search pattern. The downside, of course, is that there is only one search pattern. So if you need to query your data in more ways than just the primary key, this might not be a good model fit for you. When you're talking about key value databases, there's some basic terminology. I think the key and the value part's pretty straightforward. Another common term in this area is bucket. Bucket is a collection of key value pairs, usually a collection of things that go together. You can think of these roughly analogous to a SQL table. I'd like to say roughly analogous because there's a lot of things in the NoSQL world that do not map one-to-one with RDBMS concepts. So roughly think of it as a table, but it's just a way to organize key value pairs, assuming that everything in that bucket is semi-related. There's a namespace. A namespace is just a collection of buckets. And there's a concept of a secondary index in some of these implementations, not very many of them. In some cases, they give you one additional way to search your database apart from the primary key. A lot of times those are not quite as performant. To give you an example, if you have structured content, and your structured content is, let's say, a JSON object, and that's your value, they might allow you to provide one additional index on that structured content, that secondary search index apart from the primary key. Number one, it's not nearly as performant as the primary lookup, and secondarily, you can't do a lot of them, and you start to bog down your ultimate KV database. You start to deviate from its strong points. Its bread and butter is really that single key lookup. So when do you use KV? We talked about a couple of them already. Really, the main use case is that you require very fast reads in a high volume environment. Session stores, cache stores, e-commerce shopping carts. Another common use case is you desire an API-friendly file store. Think Amazon S3. You throw something in Amazon S3, you'll get a canonical URL identifier for that object you just threw in there. You can retrieve that object by that URL. It's great. It's very REST friendly. And it's awesome to store files in that. But if you want to look up something in S3, you can only look it up by that canonical identifier. You can't search an S3 bucket. Bad reasons to use KV. You need fast reads, but you rarely query by primary key. Or you query by a lot of things. If you have anything apart from that main primary key lookup, this is not a good choice for you. Here's kind of a broad sampling of databases that fall into the key value space. There's React, there's Amazon SimpleDB, Amazon S3, Memcache, Redis, Oracle, and Aerospike. And again, that's just a small sampling. There's quite a few of these. It's one of the bigger areas of NoSQL. The next area is document databases. Document databases are fun to talk about next because really they're just a rich multidimensional version of KV. They are a bunch of KV pairs that have been organized into a document of some sort. This is where that secondary searching really comes in. In fact, document databases are the most searchable NoSQL implementation. You can do any kind of ad hoc query on a document database. Not all of them are performant because they're not all indexed unless you make them all indexed. But it's very analogous to how you might index a table in RDBMS. The main key difference in documents over SQL databases is that the name of the game in data modeling is aggregation, not normalization. And when people start to look at a document database, they say, okay, here's a collection. That's kind of like a table. Here's a document. That's kind of like a row. And they start making all of these correlations between SQL, and then they end up normalizing their document collection the same way they would normalize a series of SQL tables. And that becomes a problem because there's no concept of a join in the document world. There are things that look like joins, but they're not. You can't, in one query, fetch things from multiple collections because it's not meant to do that. Instead of spreading your information across multiple tables in a normalized fashion, you're meant to try to jam as much as you can into a single document. And that gives a huge boost to performance when you have situations where you'd have to do multiple joins over very large tables. After a certain point in a SQL database, those joins can be costly. In this implementation, it costs nothing. You fetch a single document by maybe its primary key or a secondary key, and it comes with all the information that would otherwise be associated with that record, as opposed to having to query multiple tables and then pull it together later on. Who's used an ORM? They suck, don't they? The performance of an ORM is usually atrocious at large scales because it's doing a tremendous amount of work to take the objects that we use in programming and flatten them out into a relational database, and then repeat the process when we rehydrate that object and attempt to pull it back and bring it back into an object. The strength of a document database here is that you can save that object exactly the way you use it, and there's no flattening. So there's no ORM overhead, and the performance is noticeable. The notation for document databases can vary. It can be expressed in JSON, BSON, XML, YAML, or something of the like. The point is that it's a nested structure, a recursive structure. It also typically has a flexible schema. It doesn't force every document in a single collection to match the other documents. They can vary slightly. They can progress over time. It makes it very flexible. Here's an example. Admittedly, that's a little blurry on the screen. This is a JSON description of a Twitter message. And this can be taken verbatim and shoved into a document database. So you can see there's a list of interactions, there's a list of tags. These are things that would have to be normalized into at least 3 tables if you were modeling this in a relational world. And in document world, this is a single document. I also like to bring up the object model in this. Object databases are old. They existed before NoSQL databases were really popular. Object databases go back all the way to the 80s. They're not distinct, though. First of all, they're very rare these days. There's not a whole lot of object databases out there. And their use cases are identical to a document database. The whole point was that you could take an object you were using in an object-oriented programming language and save it directly to the database, serialize that to the database, and bring it back later. The same motivation existed there. It was avoiding the need to flatten the object and rehydrate later. So object databases, although not as common, you guys can just kind of mentally lump that into the same category as document databases because the use cases are the same. And what are those use cases? Here's a few of them. Number one, it encourages agile design through flexible schema evolution. So you can start with one definition of a model and understand that as the project progresses or the product progresses over time, this can change easily. We can just add new properties, we can remove old properties, and leave that to the application layer to sort out. So it makes it easier without having to do some of those costly alter table operations later on. Anyone try to do a big alter table operation on an enormous database and all the planning that has to go into that? Production outages and all the other fun things. Those don't exist in this world. I talked about it a little bit already, but it's a simplified model. Think of a REST API, where you go from your API layer to your service layer, ultimately to the database. How wonderful would it be if that was the same model throughout? If you could start with an object that came in on the REST API, save that object as exactly the way you use it, and pull it out exactly the same way. No need for additional transformations in the middle. In high availability worlds, that kind of performance optimization is a big win. In these highly available situations where sub-second responses are required, you want to take as much overhead out of that processing as possible, and removing the need for an ORM in the middle is a big win. Another thing is that they are horizontally scaling, typically non-blocking writes. Also a big win for the web world. You can spin up more instances of a document database to meet increased demand. Good reasons not to use it. You have a highly relational model. If your model cannot be aggregated, if you're not comfortable with data duplication, because remember, this is a non-normalized world, so you're going to have some redundancy in data as you store multiple objects. Think of an example of a customer. Let's say a customer buys a product, and we're storing all of these sales. Well, every sale transaction that we store in our document database is going to have a record of that customer, usually nested inside of each one of those sale objects. What happens when the customer's name changes? Do we want to go back and we want to retroactively update all of our sales objects to update all those customer names? In a relational world, that's fine, right? Because it points to a database record, an ID, not exactly the name. So you change the name and it updates automatically because that's how relational databases work. In a document world, that's very painstaking to go back and update documents that you've saved statically. So you have to understand your application. You have to understand if that's a trade-off that's okay to you. If it's not a trade-off you can accept, and your data really has to be relational, and those kind of operations are going to be intense, maybe you should consider something else. Another thing that you have to consider is transaction support for cross-collection updates. There are very few document databases that are ACID compliant apart from a document level. If you're looking at a collection level, meaning updating more than one document at a time, usually not ACID compliant. I usually argue that ACID is overrated in most high availability worlds. So I would like to usually have a conversation with a client about really what are our ACID requirements. But if you truly have ACID requirements, there's usually no workaround for that, and document might not be a good fit for you. Another reason that I like to bring up in every NoSQL database, if you don't have a good reason to use it, don't use it. If none of the good reasons apply to you, don't just use it because it's new and cool. Make sure that you have a use case that fits that particular model. That's not just true for document, that's true for all of these. Examples of document databases out there: Mongo, IBM Cloudant, Amazon DynamoDB, CouchDB, Couchbase. Couch is a common theme in the document world. And the newly named Azure Document DB, no longer Document DB, now Cosmos.
DB. Cosmos DB.
Not Cosmo Kramer, but Cosmo DB.
They shove that down. Cosmos or something.
The next model is columnar databases. Columnar databases are an interesting one because usually when you start talking to developers about columnar databases, you're met with an expression similar to this. There's a lot of confusion around columnar databases, and it's not because they're hard. The main reason is because the terminology is inconsistent. We can't seem to agree on what to call things. So it's a very confusing space to get into. Hopefully we can sort some of that out. There's also a kind of a weird mishmash of capabilities. A lot of columnar databases do different things. They're used in different ways. And it's really tough for developers to mentally group things together and mentally conceptualize what it is a columnar database is meant to do. Another problem, only true among older engineers, is that columnar databases are not new or unique to NoSQL. Column-oriented databases existed in the RDBMS world before NoSQL was a thing. Anybody ever play with a column-oriented database? It was just pivoted. You know, most SQL databases are row-oriented. It was taking that and turning it on its head so that the columns are primarily what you look for and search for records that match. And that's ultimately what columnar is as well. So for people who think, what's the difference between column-oriented and columnar? The differences are not really worth describing. The use cases are the same. Here's an example of some of the confusing terminology. You hear words like column family or super column family, tables, mem tables, SS tables, partitions, rows, wide rows, narrow rows, and key spaces. There's a lot of words that get tossed around in this realm, and sometimes it's hard to keep track of. So I'll try to distill some of this as best I can. A row is a series of key value pairs representing a single record. That's pretty easy to conceptualize. A partition, which is also sometimes called a column, is a collection of those rows. And there's a possible relationship between partitions and rows. If it's a one-to-one relationship, meaning every column has exactly one row in it, that's called a narrow row. And if it's one-to-many, which is the more common use, that's called a wide row. And you can think of this as, take Facebook as an example. Facebook was the creator of Cassandra. And Cassandra's first use case was an email search tool. So the primary key was all of a user's emails. And that gave you a vast selection of all of these different emails. Additionally, they could fine-tune it even further by specific keywords. Keywords in these emails that would map to a large collection of emails that go along with it. So in that case, that's the column. The column is the user and a keyword, and then all the emails that are associated with each one of those records. Though each of those emails represents a row inside of a column. And you see how that's different, right? In a row-oriented space, it's a row that has columns. In a columnar database, it's a column that has rows. And that's part of the reason partition was invented as a word, because people don't like to think upside down. People just want to, let's call it a different thing. A partition is a collection of rows. A table is sometimes referred to as a column family, but ultimately a table is a collection of those partitions. And again, roughly analogous to a table in the relational world, but very different. In the relational world, it is not possible to have this secondary dimension, this dimension of here's a key and then there's a bunch of rows that go along with it in a single table. That's one more dimension than a row-oriented database has. A key space is roughly analogous to a database in the relational world. It's a collection of those related tables or column families. The way you typically group this is by application. How many different key spaces or how many different tables does my application need? Those collection of tables represent a key space. So when would you use columnar? One very good reason is that you have a very high write throughput system. One of the attributes of a columnar database is that tables are usually written on a single continuous piece of disk space. And that's important when you want to have high performance writes, because sequential writes are a lot easier than random access. So that means these databases can consume a high volume of input, usually process it asynchronously, and allow high availability applications to continue to process that input and then make sense of that data later on. They're meant to capture a huge amount of data. Columnar databases are very often used for data warehousing. They have awesome applicability to data warehouses, and they're meant to scale to petabytes of information. Another very key part of columnar databases is that you know ahead of time how you want to interact with your database. A fundamental characteristic of columnar databases is that you model your structure, your table structure, after the query you want to run. You want to make sure that you can query by only a couple different dimensions, usually 2 or 3, and make sure that all the results that are returned from that 2 or 3 dimensional query come back in the order that you want them. It's not as flexible as a RDBMS database. It's not as flexible as document, but it is slightly more flexible than key value. Bad reasons to use columnar: you have a small data set. Really, you don't need it. If you have small data, you can model your data in just about anything. Don't worry about all the overhead and confusion in columnar if you don't have to tackle it. Your application is extremely read intensive with only periodic writes. That's the opposite of what columnar is good for. Another possibility is that you require real-time ad hoc queries over your data. You have to know those query patterns ahead of time. If you want to do ad hoc queries, you're going to end up with some very non-performant results. Examples of columnar databases: the big popular ones out there are Cassandra, Google Bigtable, and Apache HBase. Anybody who's used the Hadoop framework would probably know HBase. And Cassandra has also been a big token name in the columnar world for quite a while. Graph databases. Graph databases are one of my favorite topics to talk about. They're another model. They're also the fourth and final one. But they're a model that is often confusing as well, but for a different reason. Columnar is confusing because people can't use the same words to talk about the same concepts. Graphs are confusing because it's vast and they are legitimately complicated. For example, if I were to try to articulate a graph database, I might say it's an online transactional data store. Kevin might tell me it's an offline source for batch analytics. I might say it's a collection of nodes and edges. Alex might say it's subjects, predicates, and objects. And the kicker is that in all these cases, we would all be right. That's kind of hard to wrap your head around. It has a very vast application. Usually it can be divided along the lines of OLTP and OLAP. Anyone familiar with those two terms? Online transactional processing is used in the real-time availability world. In a web context, for example, people that are accessing data in real time, wanting to pull that information back in real time, that falls roughly in the OLTP realm. The OLAP is offline graph analytics, and the key aspect here is that they're not processed in real time. Any OLAP setting is an analytical setting. It's something we're doing in a batch context, not real-time availability. In the graph world, this is often paired with distributed computing frameworks. You might plug your graph database into a Spark or a Hadoop framework and do some mining on your data. You can't do that in real time because the queries take longer. They're bigger, but they're still very applicable and they still glean very awesome results. You just don't need to query those in real time. And both of these exist in the graph world. And that's kind of part of the confusion. Another part of the confusion is the RDF versus the graph debate. And I don't have to ask, I'm pretty sure no one's heard the RDF versus graph debate. But if anyone wants to take a guess, can someone tell me which of these models is an RDF model and which one is a graph model? That's as good a guess as any. The thing is, it's a trick question because both of these can be modeled in either one. The problem with that question is that it's stupid vocabulary. RDF and graph are the same thing. What most people call graphs are really property graphs. The property graphs are a specific type of graph, but RDF stores and triple stores are just a different type. There are three main graph models out there. There's property graphs, hypergraphs, and RDF triples. And the differences between those three go beyond the scope of this brown bag. To kind of, if you're curious, there's only one hint up here that might imply that the one on the right is a property graph and the one on the left is an RDF. And that's the fact that the one on the right has a relationship that implies it can house an alcohol percentage. If the relationship itself can have properties, that's a property graph. In RDF worlds, the relationships are just predicates, and they're just meant to be single instances that don't have properties of their own. They're just meant to define a relationship between object 1 and object 2. So that's where you get the concept of subject, predicate, and object. Those are the three components there. Again, it's all the same kind of idea, whether you're calling these nodes and edges or whether you're calling them subjects, predicates, and verbs. I'm sorry, subjects, predicates, and yeah, verbs. Doesn't matter what the terminology is. These all represent graphs, and the use cases for all three of these graph models, properties, hypergraphs, and RDFs, are the same, roughly speaking, when compared to the rest of the NoSQL world. So back to the original question, how would I define a graph? Very vaguely. I would define it as any collection of vertices and edges or nodes and relationships. And what would I call a graph database is any database that, from the user's perspective, offers graph functionality or exposes a graph model with basic CRUD operations. Now, why do I say from the user's perspective? Because there is a difference between graph databases that actually have native graph storage versus other models that kind of pretend to be graphs. A good example of this is SQL Server. SQL Server has a graph interface, but under the covers, it's still SQL Server, storing things in tables and relationships that way. So it has a graph interface, and for that, I would call it a graph database, but it doesn't have a lot of the native performance. So the difference matters, but understand that graph database is a broad term, and when people use it, don't assume how that graph is implemented. So what are the characteristics of a graph? Number one, they are very highly performant. They scale amazingly well due to a concept called index-free adjacency. And I can illustrate this. Let's take a social network. Social network is comprised of users and relationships to other users. So you have two concepts, me and my friends on a social network. And in a relational world, that is a recursive relationship, right? Because we're all people. We would likely all be stored in a people database. And if I want to find my friends, that's an easy query. It's a recursive join. I would join back on the people table on all friends that have my ID as a friend ID. But what happens if I want to find my friends of my friends? Do that next level. Still possible in SQL, but how big is that query getting now that you're 3 recursive joins in? And what happens if you want to do friends of friends of friends? You see how unruly this can get in a SQL database. And forget about the syntax, forget about how hard it is to structure the SQL for that. Let's talk about performance. The more recursive joins you have on a large table, the harder it is going to be for SQL to service that query. When you start getting into friends of friends of friends, that's where that query almost doesn't return. If you get to that fourth level, that fourth degree of separation, that takes a long time to return in a SQL database of any size. And the bigger that table gets, the slower all of those queries get at every degree of separation. Index-free adjacency is a graph principle. If I had, and this is why I wanted to put a whiteboard up here. No one online can see what I'm drawing, but that's okay. If I had friend A and friend B, and they were connected, to find my friend B list of friends and everyone that he might be friends with, because he could be friends with lots of people, to find this relationship, this does not get harder the bigger the graph grows. If I have millions and millions of other users here, it does not impact the query performance, because the principle of index-free adjacency is that you always start at one point and you traverse the links. It's not a join where we're taking separate tables together, joining these massive tables, and then trying to whittle the results of those tables down. Instead, we start at a node, we traverse that node for as long as we specify to traverse it. This is index-free adjacency. It doesn't matter how many other nodes in the ecosystem. There could be billions. The query performance is only impacted by my traversal route. So if I'm scanning, if I'm traversing this graph for a very long period of time, that could have a query performance impact. But the adjacent nodes around it that are not part of my query path do not impact the performance of my query. Does that make sense? Another thing it has is that it's flexible. Graphs are kind of naturally additive. Graphs are often used to model situations in the real world. They help us understand real world situations. We don't know how a social graph is going to evolve. We don't know how friendships are going to crop up in any kind of social setting. So these graphs are kind of predictive after a while. They tell us things that we didn't know we would know ahead of time. So they help us really map unfamiliar models. And they can change over time, because changing a graph is as simple as changing the relationships, changing the properties of an object. It's a very evolutionary concept. And again, both the structure and the schema can easily change over time. They share that in common with document databases. Agility, this is very well aligned with the agile and test-driven methodologies. It's possible to start with a certain set of requirements and allow your graph to grow over time to meet additional ones. You know, maybe right now all you're interested is tracking users and their interests in movies. Maybe you want to take that a step further and track movies they buy versus movies they watch in a theater. Very easy to evolve this model to add additional relevant information to the graph later on. Common use cases, I talked about a couple of them already. Social graphs, recommendation engines, the Netflix recommendation engine. Most of the popular recommendation engines out there are backed by graphs because it's easy to create. You just start lining things together. You start mapping things together. Products that this user looked at, products that this user actually bought, products that this user liked, rated well. Users that share certain demographic information in common with this user. Maybe there's a correlation between, because they have demographic similarities, maybe there's a correlation between the products this guy liked and the products you'll like. Maybe the buying habits of this user are very consistent with the buying habits of another user, and that can influence our decision. Again, we may not be sure exactly how this graph will grow. We can't be sure exactly how what information we can glean from it, but by growing these relationships over time, collecting as much information, relating all these objects together, we can find patterns that we didn't know existed. Which is a big part of fraud detection. Fraud detection is another use case there. Any credit card company that's notifying you of unusual behavior is usually basing that analysis on a graph, because that graph consists of your usual purchase patterns, places you buy, things you buy. where you live, etc. So if you deviate from what they consider to be a normal pattern, that's a good indication to them fraudulent has happened. And the more information they have, the more intelligent they can make an assessment. So the more information that they can use to find out what your normal pattern is, the more intelligent the graph algorithm becomes. So for that reason, as you might imagine, machine learning plays a big part in the graph realm. Teaching and training in a program, graphs are a good data sets to provide that training base. And really, if you have any highly connected model wherein relationships themselves are the focus, that's kind of the pivot from the relational world. The relationships are the focus more so than the objects. That might be a good use case for a graph database. People often ask, when should I use graph databases? I like to say when you have a graph question. And graph questions could be, for example, let's look at what a good question that's not a graph question. Let's say, how many people in this bar are drinking whiskey neat? That's not a graph question. You can ask that on any database. You can ask that on a relational database. It's a simple query to find how many people have ordered whiskey neat. But if I want to go into the bar and ask my favorite question, who in this bar is most likely to buy me a drink? That's a graph question. That's a graph question because it's not an easy answer. Who's most likely to buy me a drink? I'd have to look at who likes me. I'd have to look at who's in the bar and then realize that the ratio of people who like me and are both in the bar is 2 separate circles on the Venn diagram. That makes me sad. But it's a hard question to ask. It's more complicated than simply asking how many people are in here drinking a certain product. Another common graph question is, how many degrees of separation are there between me and Kevin Bacon? You need a social graph to traverse that. You need to figure that out. It's hard for a relational database to answer how many degrees of separation are there between me and someone else. Recursively, that's really hard to structure a query. Examples of graph databases out there include Neo4j, by and large the biggest player in that realm and probably one of the longest standing players. On the newer side, you have ArongoDB, TitanDB, and MarkLogic. OrientDB's been around for a while. OrientDB is a hybrid model. It's kind of fun. It's a mix of object databases, which I know told you guys don't exist, but it's a mix between an object database and a graph database. Kind of neat. But these are some of the big players, and again, that's only a sampling. Closing thoughts. So some important takeaways for NoSQL databases. Number one, they're not the next generation of RDBMS. When NoSQL first came out, it was extremely popular for people to start talking in terms of how can I take my relational database and fit all of it in this new NoSQL database. Part of that was because people are dumb. Part of it was because some of the vendors were being a little bit less than truthful about what their database could support. Mongo's especially guilty of this. If you ask a Mongo guy, he'll tell you how you can take your entire database and plop it into Mongo. Doesn't change what Mongo's strengths are, and some of the worst designs I've seen out there are people who have used document databases to normalize normal database and just plop it one-to-one. Every table in their relational database goes into a collection in Mongo, and that's shit. That is terrible performance. Another takeaway is that NoSQL databases are not a drop-in replacement for RDBMS. They're not the next evolutionary step. They were intended to fix a specific problem. You shouldn't replace what you have with this. It's meant to augment what you have. Along those same lines, NoSQL databases are specialized databases created to solve a specific problem. If you don't have the problem that this NoSQL database was intended to solve, there's not a lot of reason for you to use it. NoSQL databases are very powerful and useful tools designed with extreme scalability in mind. Please, please, please avoid bro SQL logic. Don't use a database because it's hip. Understand its use cases, understand what it fits in your model, and understand why you're using it. There should be a reason why you're choosing something like NoSQL. One last closing thought is it's becoming extremely common in enterprise applications to have the concept known as polyglot persistence. This is a aggregation, a collection of a lot of different databases that solve a lot of different problems. Gone is the era of the golden hammer, where we have to find one database that rules them all. In fact, I was just at a client today, not today, but yesterday, that told me that Cassandra was their NoSQL database of choice, meaning all the other NoSQL databases are equally interchangeable, so they just picked one, and that's going to be the database they use for every single use case. That's silly because Cassandra doesn't fit for everything. An example of a well-structured application might look something like this, which I shamelessly stole from Neo4j's website. It might be where we're using Redis for our shopping carts on our e-commerce application. Maybe we're using MongoDB for our product catalog and Neo4j for our recommendation engine. Very common in enterprise applications to find the right tool for the job in every use case. We talked a long time ago about microservice architectures, but that's a common solution for microservice architectures because every service can essentially own its own data. And every service would be free to choose which one of these databases makes sense for it. There was a time where this wasn't possible because of operational costs. It would be difficult to run so many different databases together because your ops team needed a working understanding of every one of the databases that it ran. In the cloud world, that's becoming less true due to the rise and increase in managed services. So we've got Redis as a managed service. We have MongoDB as a managed service, DynamoDB, DocumentDB, excuse me, CosmosDB. All these managed services out there that drastically reduce the operational cost. Now it just takes technical developer know-how and not system admin support. So now it's easy to spin up a new database, to try it out, see if it works with your application, and it's really not a large investment to have 3, 4, 5 different types of databases supporting your large-scale application. Make sense? Take that as a yes. Any questions? Yeah.
So I guess so you kind of have your data bit spread across different databases. You want to, I guess, run reporting that pulls data from different databases. Would you kind of just have a job that kind of syncs up the special data over a certain period of time?
Yeah, great question. And I'll repeat for anyone watching online. The question was, if you have a polyglot persistence environment and you want to run a batch job that aggregates information over multiple databases, what can you do to do that? The common solution for that is the notion of a data lake. There is a place where all this information kind of trickles down into, and it does serve as more of an aggregate store. This could be a data warehouse solution like HBase or Cassandra, or the Azure tool. What's that? Yeah, is it called Data Lake Analytics? Awesome. And you can use tools like Data Factory to help synchronize those different many different places on the OLTP level to aggregate down into that OLAP level. There's also other mechanisms. Event-driven architectures tend to use message queues to populate and notify the data lake of any data changes. Some things are kept in sync that way. Some applications do 2 writes. They'll save to their database and they'll also save to the OLAP data lake. There's a lot of different patterns, each one with kind of its own set of trade-offs, but the idea is that it does eventually become duplicated in the same place so that we can have one single source to run information on. There's also other ways too. If you decide not to aggregate, there are query tools out there that are meant to span multiple databases. Like in the Hadoop world, there's Hive, and Hive can actually source its information from multiple tables. Apache Drill does this as well. And a lot of these big data tools are meant to allow you to query multiple sources of information without having to consolidate that information first. So in some cases, that's a good fit. In other cases, you really do need that consolidation. So asynchronously, OLAP settings, there's a lot of different ways to get it in there. Any other questions? Cool. Well, that is it for me then. Thanks a lot. And we can close that.